Hello, everyone. Welcome to the OCP Executive Track session from Inspur. My name is Yinan Liu. I'm a customer program manager at Inspur, responsible for managing the engineering programs with our strategic SAP customers and driving the product innovation with the industry partner. Today, my topic is from OCP hardware to OCP total solution. I'm going to talk about Inspur's hardware contributions, and beyond that, the total solutions for the OCP community. First, let me give a brief introduction of Inspur. According to the Gartner report, Inspur is a top 3 server vendor in terms of shipment and revenue. We design and deploy robust, customized server infrastructure for the enterprises and for hyperscale data centers. We have strong expertise in the AI field, providing cutting-edge GPU servers and AI total solutions. We believe open innovation is the trend for efficient collaboration, so we actively participate in the open communities and drive the open platform development and adoption. Inspur joined the OCP community in 2016 and became a platinum member since 2017. We contributed many platforms, including the 2-socket nodes, 4-socket, GPU box, storage product, and the OAI system. We also lead the OpenRMC sub-project, which focuses on the areas of rack-level management. In this presentation, I will dive deep into our 4-socket solutions. Here's a recap for the 4-socket hardware product. Inspur NF8260M5, codenamed Green Mountain, was contributed in OCP Summit 2019 together with Intel. It's a high-performance 4-socket server based on Intel Purley platform with many extreme design concepts. All the hardware collaterals are open at OCP website. You could go there to download and review the design files. Here is the system overview and specification. It's a 2U head 4-socket, support 48 DIMM slots, 24 2.5 drives in the front drive bay, and 8 PCI slots plus 1 OCP NAND card in the rear. It has very optimized thermal designs. As you can see, the 4 CPUs have a non-parallel layout on the motherboard to allow better airflow. And the system fan module are sitting in the middle of the board to provide a better thermal condition for the rear components and prevent the overheat. So the 4-socket platform brings great compute performance, high memory bandwidth, and flexible storage capacity. You can get up to 112 physical cores with Intel Xeon 2nd generation scalable processors in the 2U space. It also brings cost efficiency. Using the 4-socket infrastructure can reduce your total cost of ownership compared to 2-socket infrastructure. I will talk about it in details in the next page. Let's say you have an 80 CPU workload cluster. The left side is 40 units of 2U 2-socket in 2 racks. The right side is 20 units of 2U 4-socket in 1 rack. They both have 80 CPUs, 480 DIMMs, similar storage for the workload. But using the 4-socket infrastructure, you only need half the quantity of the chassis, motherboards, fan modules, and the power supplies. Of course, the 4-socket board costs more than a 2-socket board, but it still saves a lot when you compare with 2 2-socket boards. So for the L6 barebone cost, you can actually save about 21 to 27% depending on the configurations. On the power saving side, since the 4-socket uses 1 set of fans and PSUs instead of 2 sets for 2 2-socket servers. So 1 4-socket can actually save around about 7% power consumption compared with 2 2-socket servers. Imagine how the saving would be if you have a large infrastructure footprint and runs 24 hours by 365 days. Additional savings on the network fabric and boot devices will further lower the TCO. So this is how the 4-socket hardware looks like and what benefits it brings from the hardware perspective. There will be a technology transition cost for sure to convert from the existing 2-socket infrastructure to 4-socket, right? However, we have seen that many software solutions have optimized for the 4-socket platform and have been taking advantage of the 4-socket performance value. Let's move to the application level and see how the 4-socket solution is built and optimized for certain applications. The first use case is for SAP Hana application. SAP Hana is an in-memory column store database. It consolidates OLTP and OLAP in one system. With the data volume growing tremendously nowadays, people need larger and larger database to store and manage their data. Inspur Mountain 4-socket is certified for the SAP Hana with many certification scenarios. The 4-socket brings more compute power and memory bandwidth, and by configuring the Intel Optane persistent memory, the system can support up to 15 terabyte memory. SAP HANA 2.3 is the first database management system that is fully optimized for Intel Optane persistent memory. Inspur Mountain 4-socket can provide a range of configurations that are suitable for different sizes of SAP HANA workloads. It's listed in the OCP marketplace, recommending for SAP HANA users. You probably have heard about this in Inspur OCP keynotes about SAP HANA value proposition with Intel Optane persistent memory. So Intel Optane persistent memory, I will use PMAM for short. It runs at near DRAM speed, but has much higher storage capacity than the DRAM, and is more affordable per terabyte of memory. Compared to the DRAM-only servers, the combination of DRAM and PMAM means that SAP HANA can support larger datasets on fewer servers. We can consolidate many old generation servers to fewer number of scaled-up 4-socket nodes. It could effectively simplify the server landscape and administration. The PMAM also brings a better solution for the customers. The persistent attribute of the PMAM can significantly reduce the SAP HANA application restart time and minimize the impact of system downtime. We all know that system downtime could be very expensive for the enterprises. Taking a 3 terabyte database as an example, usually 20 to 30 minutes is required for restarting the service after a system downtime, such as software patching or OS upgrading. With PMAM, since a lot of data is stored in the persistent media, the restart time could be reduced at 5 times faster than the DRAM-only servers. It's also easy to deploy a disaster recovery and backup system using the 4-socket with PMAM. These features can help to provide a better business continuity solutions for the customers. On the TCO side, 4-socket with Intel persistent memory can help save the TCO of SAP HANA implementation by lowering the infrastructure cost and by reducing the infrastructure complexity through a lower server count, a smaller data center footprint, and a simpler management. I'll use 2 actual 4-socket configurations as an example. Imagine configure A is a DRAM-only server with 3 terabyte DRAM memory. It will use 1.5 terabyte for working memory and 1.5 terabyte for database tables. Configure B is a 4-socket with DRAM plus PMAM. It will use 1.5 terabyte DRAM for working memory and 3 terabyte PMAM for database tables. So the database size on configure B is doubled, but the configuration has a lower cost than the configure A. By SAP HANA software optimization, the PMAM configuration can actually keep the same SLA. So it's safe to say that the PMAM configuration can double the capacity with lower the cost. The maximum memory size of a DRAM-only 4-socket will be 6 terabyte. That will be 48 pieces of 128 gigabyte DIMMs, and this will be a very expensive server on the market. With Intel persistent memory, we can get a 9 terabyte system with the same cost. It's a better return for such a big investment. And it has the capacity of expanding to 15 terabyte for your future demand without the need of changing hardware platforms. So using this concept, we can convert a 21-node scale-out DRAM-only infrastructure to an 8-node scale-up PMAM solutions to significantly simplify your server landscape and give you approximately 40% TCO saving. So 4-socket is really a sweet spot for the SAP Hana application, and Intel Piman has brought a memory revolution to solve the enterprise's challenges. The second use case I want to talk about is query-mounted 4-socket for Redis workload. As we know, Redis is an open source in-memory data structure store, mostly used as a database or cache. Query-mounted 4-socket server can achieve faster computing performance and lower latency. We also did some demos with the Intel team on the 4-socket, leveraging the Intel persistent memory technology and demonstrated more advanced benefits. Let's look at a Redis performance benchmark comparison between the 4-socket and 2-socket. The 4-socket Redis server contains 96 Redis instances. We'll use another client server connecting to the 4-socket to stress out the memory and perform the read and write performance test. The similar test is done on the 2-socket server. So you can see the 4-socket represented by the yellow bar has double the TPS performance than the 2-socket. In other words, one 4-socket has a better performance than the two 2-socket systems. On the right chart, we can see that the P99 latency on the 4-socket is surprisingly 10 to 30% lower than 2-socket. So this benchmark shows the great scalability of the 4-socket platforms. And then Inspur also partners with Intel team and runs the Piman Redis on query-mounted 4-socket. Piman Redis is one Redis version that supports Intel Optim persistent memory based on the open source Redis 4.0. It benefits the Redis performance by taking advantage of the Piman competitive performance and persistency. Traditionally, the key value pairs are stored in DRAM. If customer requires data durability, we can enable the Redis AOF, the append-only file feature. When this feature is enabled, the node will write all the operations that change cache data to an append-only file in the MME SSDs. But now, when configuring with Intel Optim persistent memory, we can keep the key in the DRAM, same as before, but store the values in the Piman. Since the value is persistent in the system, we can now append only the pointer or the address of the value into the AOF log file on the MMEs, rather than writing the full operations. Here are some testing data for this demo. For the DRAM-only configuration on the left, the query per second performance is around 1.8 million. And for the DRAM plus Piman configuration, running under the app direct mode, the QPS is around 5.5 million, which is a 3-time improvement than the DRAM-only config. The usage of Piman creates a tiered storage architecture. It provides a faster and persistent medium to store the value and thus resolve the MME bandwidth limitation during the writing to the AOF log files. The hardware cost increases about 40% by adding Piman, but it can achieve 3 times better performance. This can significantly improve the performance per price, especially in the write-intensive applications. This demo is also shown at Inspur virtual booth for this OCP Summit. Please come and take a look for more details. Next, I'd like to talk a little bit about Inspur OpenRMC contribution. Inspur has been participating in the OpenRMC sub-project group since 2018, and we currently co-chair the project. The goal of OpenRMC is to define a unified rack management controller interface and have a unified rack level resource management implementation. Here is how the high-level architecture looks like. The southbound interface with hardware and collects the hardware information using the Redfish API. The RMC controller will consolidate the system information such as component inventory, firmware, thermal monitoring, power control, etc., and provide a web UI to the data center administrator. The controller will also provide a northbound interface to a management application using the Redfish APIs. Inspur is working with industry partners to unify the Redfish API spec And we have contributed our RMC web server and web UI source code to the RMC repository. So if you are interested in this topic, there is a separate session of OpenRMC overview and update. It's an engineering workshop talk scheduled on May 13th, and the Inspur architect who co-leads the project will share the latest updates of OpenRMC and present a demo of one of the RMC controller user interfaces. So we talk about the 4-circuit hardware. We talk about SAP Hana with Intel Piman and the OpenRMC rack management. Here is the complete package for the customer. Inspur OCP rack solution for SAP Hana is a fully integrated rack level solution, combining the OCP recognized hardware with validated software, allowing customers to manage resource in an efficient and scalable manner. It is a combination of the OCP hardware nodes, the Cream-mounted 4-circuit we talked before, SAP Hana software, and OpenRMC rack management toolsets. Cream-mounted 4-circuit will enable large memory capacity and lower platform TCOs for this SAP Hana deployment. And OpenRMC can be used to manage multiple nodes across the racks. This consolidated solution can help small and medium-sized data center customers to greatly reduce their IT operation and maintenance cost, simplify their rack management, and improve the deployment efficiency. So to wrap up for this session, we have seen that the 4-circuit solutions are more and more adopted in the traditional enterprise workloads, especially in the large database and high-performance computing applications. Inspur is investing and leading the OpenRMC development for a unified rack management implementation. We look forward to seeing more open hardware that can comply with OpenRMC. It's great to see a lot of open hardware in the open community. We believe that delivering the total solutions to customers will accelerate the adoption of open technologies. That's all for my presentation. Thank you all for your time joining this session. For more information, please visit our OCP virtual booth and our website at inspurSystem.com. Thank you very much.
Hello, everyone. This is Iman from Inspur. Thanks again for joining the session. So I will be here for a while to answer any questions regarding the 4-circuit solutions and Inspur solution. So please feel free to jump to the question. Thank you. Please also note that we have a live demo at Inspur booth for the Redis workload we talked about in the presentation. So you can visit our Inspur booth at the expo hall and take a look at that. We're also showing an OpenRMC demo in the Experience Center. So, I saw a question asking the logs for the Redis, if it's written back to the PMAP, if it's written back to the SSDs, or it stay in the PMAP. So the answer to your question is, when we have the AOF feature enabled for the Redis, all the operations, including the write and delete operation, will be recorded to the AOF log file in the MME. But traditionally, you have to put all these data in the MME. But when you are using the PMAP, since the value is already in the PMAP, right, it's persistency media. So you only have to copy the key and the address of the value to the SSD. So this kind of resolves the MME bandwidth burden. So it helped to improve the performance a lot. And it's for every operation, right? So it seems about good for this session. I just want to thank you all for joining, and thanks OCP team for the summit. Thank you.